Hello friends, today let's look at the algorithm for finding the maximum element from each subarray of size k. This algorithm runs in order of n time. So the problem statement is, we are given an array of integers and an integer k as input. We have to write a program to print elements with maximum values from each possible subarray of size k. The subarrays would be formed from the given input array. For example, if the input is this array and input k is 4, then the output sequence printed should be this sequence. Note that the first subarray of size 4 would be formed by these 4 elements 9, 6, 11 and 8. The maximum element for this subarray is element 11, and therefore the first number that is printed in the output sequence is 11. The second subarray of size 4 would be formed by these 4 elements 6, 11, 8 and 10. The maximum element in this subarray is element 11, and therefore the second number printed in the output sequence is 11. In the very similar manner, we have generated the remaining output sequence. Now let's try to solve this problem. So before jumping onto the algorithm, let's understand what is a dequeue data structure. We'll be making use of this data structure in the algorithm. So a dequeue data structure gives you flexibility to add and delete nodes from both ends of the queue. This dequeue data structure can be implemented by using a doubly linked list with a head pointer and a tail pointer for operating from both ends of the list. For example, in this doubly linked list, we have maintained both head pointer and tail pointer, using which we can add and delete nodes from both ends. Now let's try to understand the intuition behind the algorithm. If the list denotes the dequeue data structure, then we are going to make use of following 3 rules in the algorithm. The first rule is, we add indices of array elements in the list. Note that we are not adding array elements themselves in the list. The second rule is, we keep only those indices in the list which are part of current window of size k. And the last rule is, we keep only useful indices in the list. For deciding if the index is useful or not, we are going to use this particular rule. Let's try to understand these rules using an example. So the list denotes the dequeue data structure. We add index of first element, that is index 0 in the list. Note that this index 0 corresponds to element 9, right? When we are looking at the first 4 elements of the input array, first 4 elements, we are basically looking at the first subarray or first window of size 4. Now after adding index 0 in the list, we add index 1 in the list, which corresponds to element 6, right? This corresponds to element 6. Now while adding index 2 in the list, which represents element 11, note that this element 6 is less than 11, 6 is less than 11. Therefore, we can be sure that this element 6 cannot be the maximum element in first subarray of size 4. Also note that in any subsequent subarray of size 4, let's call that subarray sub of size 4, if that subarray contains element 6 in it, then that subarray will have element 11 in it, right? Therefore, in any subsequent subarray of size 4, element 6 cannot be the maximum element because we know that element 11 will always be there. This basically makes element 6 and its corresponding index 1 as not useful. As a result of that, we remove this from the list. We remove this index from the list. Now the modified list has only 2 indices in the list, index 0 and index 2. Now again note that element 9, which corresponds to index 0, is less than 11, right? Therefore, we can be sure that 9 cannot be the maximum element in the first subarray of size 4. Also, in any subsequent subarray of size 4, if element 9 is present in it, then element 11 will also be there. Therefore, this 9 can never be the maximum element in any subsequent subarray of size 4. That makes this element 9 and this index 0 as not useful. As a result of that, we remove this index as well from the list. We remove this index 0 from the list. Now the modified list has only index 2 in the list. Note that while adding index 2 in the list, we have removed index 0 and index 1 from the list. For that, we have made use of this particular rule where if the element corresponding to an index in the list is less than the current element we are looking at. The current element we were looking at was 11. We remove that index from the list. If the element corresponding to an index in the list is less than current element we are looking at. The elements corresponding to an index in the list were 9 and 6. Both were less than 11. Therefore, we removed their indices from the list. This is because the element corresponding to this index, that is the removed index, can never be the maximum element in the current window or in any subsequent window of size k. Now after adding index 2 in the list, we look at element 8 which corresponds to index 3. We add that in the list. This index 3 corresponds to element 8. 11 is not less than 8. Therefore, we don't need to remove this index 2 from the list. Now, while adding index 4 in the list, which corresponds to element 10, note that this element 8 is less than 10, 8 is less than 10, and therefore we know that this 8 cannot be the maximum element in current window which includes element 10 or in any subsequent window of size 4. Therefore, we remove this index 3 from the list. Now we check if 11 is less than 10. It is not. Therefore, we don't need to remove index 2 from the list. Now the modified list has only two indices in it, index 2 and index 4. Now, while adding index 5 in the list, which corresponds to element 5, we check if 10 is less than 5. It is not. Therefore, we don't remove this index 4 from the list. 11 is also not less than 5. Therefore, we don't need to remove 2 from the list as well. So we add index 5 in the list, which corresponds to element 5. Now, while adding index 6 in the list, which corresponds to element 4, we are basically looking at subarray of size 4 ending at element 4, which is at index 6. So subarray of size 4 would be formed by these 4 elements, 8, 10, 5 and 4. Element 11 would not be there in the current subarray of size 4. The index of element 11 is 2, right? Now our second rule states that we only keep those indices in the list which are part of the current window of size k. Element 11 and its corresponding index 2 are not part of the current window of size 4. Again note that the current window of size 4 has elements 8, 10, 5 and 4 in it, and therefore element 11 is not part of it. We remove this from the list by using this second rule. We remove this index 2 from the list. Now we check if 5 is less than 4. 5 is not less than 4. Therefore, we don't need to remove index 5 from the list. We again check if 10 is less than 4. If 10 is less than 4, it is not. Therefore, we don't need to remove index 4 from the list as well. The modified list has index 4, 5 and 6 in it. Now continuing with the intuition of the algorithm, until this point, we have looked at this portion of the array, right? The last element looked was element 4, and the state of the list is that it has 3 indices in it, index 4, index 5 and index 6. We have kept only useful indices in the list, and by doing that, we have maintained the state of the list in such a way that array elements corresponding to the indices in the list are sorted in decreasing order. Note that in this list, element 10, which corresponds to index 4, is greater than element 5, which corresponds to index 5. which is greater than element 4, which corresponds to index 6. So, elements corresponding to indices in the list are sorted in decreasing order. We are maintaining this state by keeping only useful indices in the list. Also note that we are removing those indices from the list which are not part of current window. Overall, what we are trying to make sure is that the element corresponding to the first index in the list is the largest element in the current window of size k. The current window of size k is now 8, 10, 5 and 4, right? Because the last element we looked at is element 4. Now, the first index in the list is 4. Its corresponding element is element 10, right? And this element 10 is the largest element in the current window of size k, of size 4. So this is basically the intuition behind this algorithm. Please don't worry if you haven't completely got the intuition. Once we look at the algorithm, we are going to run the algorithm on the input again. Now let's look at the algorithm. This algorithm is a two-stage algorithm. In the first stage, we add indices of first k elements into the list or dequeue. Here, the list denotes the dequeue. In the first stage, for int I is equal to 0, I less than k, for int I is equal to 0, we remove all indices j's from the rear end of the list for which array of j is less than array of I. The current list is empty now, therefore step 1 will have no effect. In step 2, we add index I at the end of the list. I is 0, therefore we add 0 to the list, right? This 0 corresponds to element 9. Now I is incremented to 1. This corresponds to element 6. We remove all indices j's from the rear end of the list for which array of j is less than array of I. We check if 9 is less than 6. It is not. Therefore, we don't need to remove index 0 from the list. In the second step, we add index I at the end of the list. I is 1. So we add it to the list, right? This corresponds to element 6. Now I is incremented to 2. This corresponds to element 11. Starting from the rear end of the list, we check if 6 is less than 11. It is. Therefore, we remove this index 1 from the list. Now we check if 9 is less than 11. It is. Therefore, we also remove index 0 from the list. And in the second step, we add index I. I is 2 at the end of the list. So list now has only index 2 in the list, which corresponds to element 11. Now I is incremented to 3. This corresponds to element 8. We check if 11 is less than 8. It is not. Therefore, first step will have no effect. In the second step, we add index I. Index I is 3 now to the end of the list. This corresponds to element 8. After adding index 3 in the list, the first stage of the algorithm is completed, where we have added first 4 elements or first 4 indices in the list. After the completion of stage 1 of the algorithm, the first index in the list corresponds to the largest element of current subarray of size k. The first index in the list is 2. The corresponding element is 11, and 11 is the largest element for first subarray of size 4, right? In the subsequent stage of this algorithm, we try to maintain this state of the list, right? Let's now look at the stage 2 of this algorithm. In this stage, we add indices of the remaining elements into the list while maintaining the right state of the list, right? For that, we make use of following steps. For I is equal to k, I less than n. For I is equal to k, so I would be equal to 4. The first step is print the element corresponding to the first index in the list. The first index in the list is 2. Its corresponding element is 11. So we print it out. I'll write output at the bottom. So output would be 11. Because we know that the first index in the list corresponds to the largest element of current subarray, we are using step number 1 for printing the maximum element from the last seen subarray of size k, right? Now in step number 2, we remove all indices from the front end of the list which won't be included in current window of size k, right? So currently I is equal to 4. So I is pointing here, right? The 4 indices that will be included in current window of size 4 will be I is equal to 4, 3, 2 and 1, right? So starting from the front end of the list has index 2 in it. Index 2 is part of the current window of size 4. Therefore, we don't need to remove index 2 and step 2 will have no effect. In step 3, we remove all indices j's from the rear end of the list for which array of j is less than array of I. Note that in step 3, we are basically removing the non-useful indices from the list. So starting from the rear end of the list, starting from element 8, we check if 8 is less than 10. It is less than 10. Therefore, we remove index 3 from the list, right? So this index 3 is removed from the list. Now we check if 11 is less than 10. It is not. Therefore, index 2 will not be removed. And finally, in step number 4, we add index I at the end of the list. So I is 4. We add it to the end of the list, right? The modified list now contains index 2 and index 4 in it. This index 4 corresponds to element 10. Now I is incremented to 5. So I currently points to element 5, right? In the first step of the for loop, we print out the element corresponding to the first index in the list. That element is 11. So we print that out in the output sequence. In the second step, starting from the front end of the list, that is from index 2, we check if it is part of the current window of size 4. Now we are currently at I is equal to 5, right? The current window of size 4 will have I is equal to 5, 4, 3 and 2 in it. Therefore, index 2 is part of the current window and we don't need to remove this index from the list. In step 3, starting from the rear end of the list, we check if this 10 is less than 5. It is not. Therefore, we don't need to remove index 4 from the list. Once we establish that 10 is not less than 5, we don't need to compare other elements in the list with 5. In this case, we don't need to compare 11 with 5. Why is that? That is because we know that the elements in the list are arranged in the decreasing order. So 11 is greater than 10, right? Now because the elements are arranged in the decreasing order, once we establish that the element ej is not less than a of I, we don't need to compare other elements which are located to the left of ej, right? So in this case, our ej would be 5 and the element located to the left of ej would be element 11, which corresponds to index 2, right? Note that the point that we have just discussed helps in reducing the time complexity. So we are at I is equal to 5. In step number 3, we compared 10 with 5 and found out that 10 is not less than 5. Therefore, step 3 had no effect. In step 4, we add index I to the end of the list. So we add index I to the end of the list, right? This corresponds to element 5. Now I is incremented to 6 in the next iteration. So I is 6. In the first step of the algorithm, we print the element corresponding to the first index. That element is 11. In the second step, starting from the front end of the list, we check if it is the part of the current window, right? So I is 6 now. The current window will have I is equal to 6, 5, 4 and 3 in it. Index 2 is not part of the current window. Therefore, we remove this from the list. Now, I is equal to 4 is at the front end of the list and is part of the current window. Therefore, it will not be removed. In the step 3, starting from the rear end of the list, we compare if 5 is less than 4. 5 is not less than 4. Therefore, step 3 will have no effect. Again note that once we establish that 5 is not less than 4, we don't need to compare other elements with 4 because the elements are arranged in decreasing order. Now, in the final step, we add index I to the end of the list, right? This corresponds to element 4. Now I is incremented to 7, which corresponds to element 13. I is incremented to 7. Now in the first step, we print the element corresponding to the first index. That element would be 10, right? So this is printed in the output sequence. In the second step, we check if the front index in the list, which is 4, is part of the current window of size 4. Current window of size 4 will have I is equal to 7, 6, 5 and 4 in it, right? So I is equal to 4 is part of the current window. Therefore, step 2 will have no effect. In step 3, starting from the rear end of the list, we check if 4 is less than 13. It is. Therefore, we remove this from the list. Now, the rear end of the list points to index 5, which corresponds to element 5. We check if 5 is less than 13. It is. Therefore, we remove this index from the list as well. Now, rear end of the list points to index 4, right? And corresponding element is 10. We check if 10 is less than 13. It is. Therefore, we remove this index from the list as well. At this point, our list becomes empty now, and step 3 will have no further effect, right? So in step 3, we have removed index 4, 5 and 6 from the list. In step 4, we add I to the end of the list. I is 7, so we add it to the list. So the modified list now has only one index in it, which is index 7 corresponding to element 13. Now in the next iteration, I is incremented to 8, which points to element 93. So I is incremented to 8. The first step of the algorithm is we print the element corresponding to the first index. The element corresponding to the first index is 13, right? We print that out in the output sequence. In the second step, we check if the front index in the list is part of current window. I is 8. So I is equal to 8, 7, 6 and 5 would be the part of current window. So second step will have no effect. In the third step, starting from the rear end of the list, starting from element 13, we check if it is less than A of I. A of I would be 93. So 13 is less than 93. Therefore, we remove this index from the list. So this is removed from the list. The list is empty now. Step 3 will have no further effect. In step 4, we add index I. Index I is 8 to the end of the list. In the next iteration, I is incremented to 9, which points to element 14, right? Now, we print the element corresponding to the first index. That element would be 93. In the second step, starting from the front end, we check if 8 is part of current window of size 4. It is part of current window. Therefore, step 2 will have no effect. In step 3, starting from the rear end of the list, we check if 93 is less than A of I. A of I is 14, right? So 93 is not less than A of I, and step 3 will have no effect. In final step, we add index I, that is 9 to the end of the list, right? This corresponds to element 14. When value of I becomes equal to 10, this for loop is terminated. Note that in the first step, where we print the element corresponding to the first index in the list, we are basically printing out the maximum element from the last sin subarray of size k. For example, when value of I is, let's say, m, then in the first step, we are printing out the element for subarray ending at index m-1, right? So because of that, once the for loop is terminated, for the last subarray of size k, we need to execute this particular step to print out the maximum element. For the last subarray of size k, We need to print the element corresponding to the first index for printing out the maximum element. So after execution of this step, we print element 93 because the first index in the list is 8, corresponding element is 93. We print that out in the output sequence. This completes the execution of this algorithm. Hopefully the intuition behind this algorithm is clear now. Now let's look at the time and space complexity of this algorithm. Note that in this algorithm, every element is compared at most twice for remove operation from the rear end of the list, and every element on an average is compared only once for remove operation from the front end of the list. Therefore, for every element of the array, there are constant number of operations that are being performed, making the time complexity as order of n. I highly encourage you to find out as to why these two statements are true. At any point of time, the maximum length of the list that we are maintaining cannot exceed k. Therefore, the extra space used by this algorithm is order of k. This completes the explanation for this algorithm. If you have any doubts or queries, please let us know in the comment section below. You can check out our website www.ideserve.co.in for the web post which has complete implementation for the algorithm. Thank you and cheers.